back, everybody. We're going to run through a whole gamut of things. A lot of this is kind of review. There's a new thing I'll give to you, Rao-Blackwell. I don't think we'll get to the proof today, but the proof only takes about 3 minutes. So it's another one of those super easy, kind of obvious proofs. But I think the real insight comes from an example or two. So we'll probably run through that next time. I want to talk about Bayes' risk a little bit, and I want to recap on Cramer Rao. And I'll say a bunch of stuff. I'm also going to give you some exercises you can work out at home. So things that are just good practice. Anytime I see an identity, and I don't know it's true, or I don't know where the proof is, I try to work on it for a little while. So this isn't a passive class. You can't just watch. You can go, okay, I think I get that. That makes sense. That's good if you see things and you go, yeah, I get it. But can you play? Can you do it yourself? There's only one way I know to figure out if I can do something myself, and that's to do it. So, I'll say a few things, but there's lots of exercises you'll want to work through. If you're ever looking for exercises, you don't have enough practice, play around with these things and show it's true, or show what the lower bound is in various cases on distributions that you're familiar with. And so you can always just kind of recycle the examples. Do it for a hierarchical model if you want to really challenge yourself. So sometimes these problems can be hard. Sometimes not so much if you're familiar with the distribution. So it'll also give you distributional insights, help you to remember everything that you're supposed to be remembering. It's my best advice to you is practice. Okay, so Cramer Rao, we proved this last time. I just want to walk through the steps real quick since we're a little bit rushed. So the first thing we did, step 1, is we showed that the expectation of the log, and I say likelihood simply because I take the derivative with respect to theta inside of here, but I kind of understand that we're operating on both theta and x in this example. But as soon as I start operating on theta, I usually say likelihood. Of course, this is the functional form of the sampling distribution. If you think of it as a likelihood and you plug in the likelihood function right there and you forget the normalizing constant, or you put an arbitrary normalizing constant in here, keep in mind that as soon as I take a derivative with respect to theta, it's going to disappear. So the likelihood, the normalizing constants would go here. So if I take the logarithm of it, it's going to be some additive form of it. And if I take the derivative with respect to theta, it's going to go to 0. So if you do plug in the likelihood function, no problem. Everything will work out just fine. So we showed that the expectation of the derivative of the log likelihood is equal to 0. We did that first. So I'll let you recap that from the last lecture. It's up online. I want to take a step back before we run into step 2. And I'm going to ask you kind of a trick question here. Is this true? Is this statement true? Feels like it. Let me ask you a different question. Is this statement true? Feels like it, right? I proved it, right? Somebody help me out. It's not necessarily true. It's a big assumption here. So, this is true if this is true. The derivative of theta of the expected value, and I'll write this down. And there's a lot of ways that you can play around with this, but maybe I'll write down Wx. There's a few different conditions that I could choose. They're all identical to each other. Once I start understanding things like that, then I feel like I get things. And I'm like, oh, there's this other way to write it, but it's the same. So you want to get to that point. So this is over x given theta right here. And we need this to be able to slide right inside. So dt theta Wx fx given theta dx. So we needed needed that thing to be true in the first place. So I need to be able to slide that derivative through the integral. So essentially, I need to be able to just take this thing and be able to swap them back and forth. That's Houdini's theorem in this case, for this function. It's not always true. And Cramer Rao does not apply to cases where it is not true. There's a lot of hard problems if you've got boundary conditions that depend on the parameters. That always makes the problem harder. And these sort of results aren't true and they're not useful to us in proving maybe you have the best estimator that's really hard. Could be the case. But if this condition is true, which is true for a lot of distributions as well, then you can use this. I will point out all the asymptotic stuff that you might learn about if you're an asymptotic frequentist. If you have boundary conditions that depend on the parameters, a lot of times you need n to be extraordinarily high before you can proceed. Okay, I'll just point that out. So our next step was just to apply Cauchy-Schwarz. So we proved this. This is true if this thing is true, the condition. So if star is true, then this is true. And I slid that derivative through right there when I did that. So the proof of that depends on that being true in the first place. There have been a lot of examples. When I was in graduate school, I'd start applying this stuff sometimes. I'd notice I could find a variance for some estimator that was smaller than the Cramer Rao lower bound. The Cramer Rao lower bound is supposed to tell me what the smallest thing could be. And then I go back and I discover, oops, Cramer Rao doesn't apply. So those are good examples to work through. I'll give you one after we run through this proof one more time. The second step, step 2, was to apply Cauchy-Schwarz. So there's really just 2 steps in this proof. Show that thing is true. Make sure you adhere to the condition on Cramer Rao, and then apply Cauchy-Schwarz. We're going to apply Cauchy-Schwarz to these 2 arguments, Wx and the derivative of the log likelihood. Cauchy-Schwarz said something about this function right here, the variance. Oh, and this is covariance squared. The variance of Wx is in the denominator, and then we have the variance of the derivative of the log likelihood. Cauchy-Schwarz said something about this. It says that this is bounded by 1. That's always true. So Cauchy-Schwarz always works. Do you want to think about correlation just as an add-on? So this is a covariance function. This right here is a correlation squared. So I'm squaring the correlation. Correlations are covariances of standardized variables. So subtract off the mean, divide by your standard deviation, take the covariance of that. That's also equivalent to correlation. So standardized stuff, the correlation squared is less than 1. You can go back and recap that for yourself, convince yourself that that's true. Once you know it's true, you can use it all the time. Then we just have to recognize all of these terms. Like in here. So the variance of Wx, that's the thing we're playing around with and thinking about. So the variance of Wx, we just pulled over here. And then we rewrote these terms right here. I just have to remember what covariance was. And I wrote it out in terms of expected values. So while functions in statistics, many of them can be expressed as expected values. So, which is kind of cool. So I like expected values. I can always estimate things, expected values of things if they exist by doing Monte Carlo experiments. Anytime I see an expectation, I think Monte Carlo, sweet, I've got a computational approach for doing this. All just central limit theorem stuff. But this is going to be the expectation of Wx times this derivative, logarithm f of x, given theta. We wrote this down. We knew what this was. When we went and we proved step 1, we were able to show what this whole thing was. We had a different way of writing it down. I'll ask you about that in a second. This is going to be minus 2 expectations that are multiplied into each other. This one is going to be Ws, that expectation, and this one is going to be the derivative of the log likelihood. So what we did is we recycled our step 1. We got rid of this right here. So this ends up just being the first term. We do the same thing down below. This variance is going to be an expectation of the derivative log likelihood. It's going to be squared. And then it's going to be minus something that we already know is 0. It's going to be the expected value of the derivative of the log likelihood. Squared. Oops. This is going to be all squared. So this thing was 0. We're left with that. This thing right here is what we see right there. Those are the same things. This is the Fisher info. Some people will call this the expected Fisher info. Some people will do this empirically. If you have data points or something like that and you're trying to estimate a bound on variance, you might plug in your actual data points and change that expectation into a sum. Some people will call that the Fisher info, but that's the empirical Fisher info. This is the expected one. The empirical one will converge to the expected one. So if you're in a regression class, you might be plugging data in and not doing an actual integration. This thing right here that we wrote down, we had written down the numerator a little bit differently. This right here is going to be equivalent to this. And we get that out of step 1 when we show those. So that was our first step. So the only thing that's a little bit complicated about this proof is we keep recycling things that we know, and we use them like 3 or 4 times in this proof. And so the little pieces that we know, we keep recognizing, oh, that's 0. This other thing can be written a little bit differently. That's all in your book, and you'll want to recap that. The only thing that's a little bit different from the book and the way I proceeded is they use, when they prove this step, they use Wx, and then they turn Wx into 1, the function 1. And that usually freaks people out. It's like Wx was an estimator before. How do you pick it to be 1? You can pick it to be anything as long as you're writing it down all very generally, and then later on they use it as an estimator. And that's why I went and I said, I proved this statement using some arbitrary function, and then I subbed in 1 for that arbitrary function, and then I shoved our estimator into that function. So if you want to recap of that, it's all on video. It's all in your book. So probably a little bit of study of this will go a long way. I often ask people to prove this on finals, stuff like that. It's important and actually you want to remember how to do it. So I kind of like the central limit theorem proof. I often ask people that. A lot of remainder stuff, Taylor's method, limits are being taken, and central limit theorem is super useful. Use it all the time. Also use this Let's look at an example, but before I do that, I want to discuss the I.I.D case of this. I'll write it down over here. So Cramer Rao is this statement. And I want to point out real quickly, this is all of my data. So if we're thinking about I.I.D replicates or something like that, this would be an n vector of data points. And so this simplifies in the I.I.D case. You can kind of see it. It's going to show up here, right here. So think about what the likelihood function would look like if I ended up having log f of x given theta This is just going to be the logarithm of the product. I goes from 1 to n, fxi, given theta. And this is going to be equal to the sum over I, 1 to n, of the logarithm of fxi, given theta. Okay, so instead of writing this thing down right here, I can replace this with a big sum. Derivatives are linear operators, so I can switch the order of my derivative and my sum. That's always true. So I can always do that. It's only when these integrals right here are over like infinity or something like that, or the parameters on the bound of the space, that maybe Houdini's doesn't work. But with finite sums, Houdini's always works. You can interchange the way you add things up. Doesn't matter which way you add things, just as long as everything gets added in. And so I can rewrite this right here, and I can rewrite the denominator in terms of this sum. And I'll just do that real quick. So Cramer Rao is going to say the variance, write it down here. Some estimator, probably want to plug all my data in. This is going to be bounded by the expected value right here, derivative, and I have two choices. I can either write in all of my data right here, or I can just plug in one data point into this thing. Either way, think about the normal example. So if I were going to estimate mu in a normal example, I'm probably going to use x bar. And the expected value of x bar is mu. It's unbiased. The expected value of each xi is also mu. It's unbiased. N doesn't show up there. So the bias level doesn't depend on n. So if I've got some sort of an estimator with some amount of bias to it, whether or not I plug in one data point here or all of the data, I get the same answer. So, but the denominator can be written a little bit differently. So I can write down my n right here, and then I can write down my x, my expected value derivative of the log likelihood. I'll be a little bit more specific in a second. This is going to be squared in here. So this is my number of data points. And this is just a single observation, 1 point. Right there. So I can either plug my n in and get it through here, or I can just factorize out the n right here and plug in just 1 point right there. I'll show you an example in a second. Where's that n coming from? It's this sum that's sliding out in front. I sum it up n times, I'm multiplying by n. That's a fairly obvious result, but it's useful. I'll also show you one more thing. This is something you might want to show at home. Again, you're going to need to recycle our assumption for this to be true. So if our assumption is true, Houdini's holds. If I can interchange the order of the integral and the derivative, then I can use this result. So I can write down expected value derivative with respect to theta log likelihood squared is equal to the expected value of the second derivative of the log likelihood. And there's a minus sign out in front. Try to help you remember that that minus sign is there. So it turns out this thing is always negative. So I need the minus sign here. It's very easy to rationalize. This is always going to be positive right here. How do I know? It's the expected value of something squared. It's got to be positive. So if you ever are using these formulas and you come up, if you use this one, for instance, and it doesn't turn out to be negative right here, you made a mistake. I kind of like looking at these two things in different ways. And so this is if star is true. You can prove this. So you'll end up recycling that. Here's how you prove this. Work out both sides and show they're the same. So write them out in long form and show that they're the same. And what you'll wind up with is an extra term over here that you will know is 0 because of this. I'll let you walk through that. So these look the same. And if Houdini is true, this thing will be 0 and one of those terms will cancel out. Sometimes I like using this form. Sometimes you see people write down Fisher's info is this, but technically this is Fisher's info. This is always true. That's Fisher's info. So if my assumption is true, I can start using this form. So this makes me think about things when I see these equations. They're not just equations to me, they're concepts that I can think about. This is always positive right here. And we've just figured out in the unbiased case, the unbiased case is when the numerator is 1. Right here, because this will be theta. Derivative of theta is 1. 1 squared is 1. So what we've learned is that the inverse of this thing right here is the bound on variance. That's kind of cool. So Fisher's info is a bound on variance. Asymptotic frequentists will oftentimes use that as their variance, and they'll limit into it. I happen to not be an asymptotic frequentist, so I don't use it this way, but I have seen it used that way many times. Okay, this side right here, I think about totally differently when I see it. I can't tell that this is negative just by glancing at it. That wouldn't have been obvious for me. I just happen to know that it's always negative because this thing is positive right here. But the second derivative is measuring curvature of the space. And the curvature of the space has something to do with variance. So if this is a bound, the inverse of this is a bound on variance. Say bound in the unbiased case. This is a bound on variances. Then this thing right here is also bound on variance because they're equal. So this is the curvature of the space, the expected curvature of the space. So if the curvature is really big, it means it looks like this. It's really peaky. So curvature big means very little variance. If the curvature is really small, i.e. it looks like this, so curvature big, you just draw pictures since I'm picturing this in my head. So this is curvature big. for me, I always like to think about these things. I like to have some grounding in it that I can kind of feel like I get what's going on. That makes sense to me. And so that's kind of cool. So the expected curvature inverted, of course, straight line sign on there, is a bound on variance. And I think conceptually that makes sense. So it just so turns out that sometimes it's tight and it's exactly right. Let's look at an example where that's true. This is just a little thing for you to think about. So I'll just make a note, maybe show this.
Shouldn't we say the inverse of the expectation? Expected curvature, like the inverse of the expected curvature? Or the...
Yeah, that's what that says, I think.
Okay.
Cool. Okay, let's look at an example. And this is where Cradle Route kind of comes in. It answers questions like this. Which estimator is better, and do I have to keep searching for a better estimator? I kind of like problems where nobody really knows the answer because you can always kind of improve on it. Come up with something, I can beat that. And research continues. So there are a lot of problems that are so complicated, we can't apply Cramer Rao, and nobody knows what is optimal. So sometimes people might put down optimality conditions that are easy to solve, and they'll come up with an answer that way. But maybe that's not the optimality condition that you want. So they're proceeding as a mathematician, not really a statistician in those cases. So I do like problems where stuff like Cramer Rao doesn't hold because it gives me a research career. That I get to tackle it in lots of different ways. Problems where Cramer Rao applies in the exponential family, everybody already knows this. So this is classroom material. So I use this thing all the time, but I can't do research with it. So I do like cases where Cramer Rao doesn't apply, but let's look at a case where Cramer Rao does apply. So example, xi's, let's say I.I.D, come from a Poisson with parameter lambda. And I should probably be polite about all of this and tell you what these parameters are. So this is xi's are going to be counting numbers. 0, 1, 2, up to infinity. And you can think back to your probability class. You know, what are these distributions used for? This is what I would consider the fundamental counting distribution. So it's got some issues, but it's kind of the basis for all counting distribution models. It's a limit of a binomial. As n goes big and p goes small, so sometimes people call these rare event models, where you're counting rare events. Lambda is positive. I suppose I could take lambda to be 0, but it's only going to give me the 0 count if I did that. I probably wouldn't write down a distribution if I were doing that, so I would say lambda is positive. Nothing horribly fails if you put lambda 0 in here, but it doesn't make sense to talk about things with that are random, that never change. I think even though that is a random variable. So the constant number of 1 is a random variable. It's just not very interesting to talk about it that way. So the constant number of 0 is a random variable, but it's not very interesting to talk about it that way because it never varies. Okay. We know that the expectation of everything is lambda. Right here. We also know the variance of everything is equal to lambda. So the Poisson model has the variance is equal to the expectation. You might want to ask yourself, does that always make sense? And I don't think it always does. But can somebody just kind of tell me intuitively why it might make sense if you're counting things, why the variance would increase as the expected value increases? This is nothing like a normal where those parameters are very separate from each other. Think about if you were counting something if I gave you a big bucket full of apples, and I put 5 apples in each bucket, and I asked you just to confirm that there's 5 apples in each bucket, so you go through, 5, 5, 5, 5, 5. Every once in a while, you might count and make a mistake. Oh, this one, oh, shoot, I didn't see that apple over there. There are actually 6 apples in there. You make an error. But if I put 5,000 apples in every bucket, and I asked you to count through, or if I said, I actually didn't put exactly 5,000 in each one, I'm a little bit sloppy, I just filled the buckets up, these barrels or whatever, apples. And I asked you to go through and count them, the more apples I put into these buckets, the more mistakes you would make. And so as we count things, we tend to make more and more errors. That kind of makes sense. So, more things I want to count, more errors. It turns out in a counting model, the variance should never be smaller than the expectation. So it should never go down. And if you ever have a case where you've computed something and the variance was much smaller than the expectation, you should not be modeling that with a Poisson distribution. Just want to point that out. It's a fundamental error. So, turns out in exponential distributions for counting, that can never happen. And so I would tell somebody if they came in and said, hey, look, I computed this, I have this data right here in the variance, I did an empirical calculation of variance, and it's much smaller than the expectation. What I would tell you is it's not Poisson. It's not from a one-component model. It's probably from a mixture model or something like that. And so you need to model that differently. However, it's quite often the case that the variances can be larger than the expectations. And in those cases, what you usually do is you take a scale mixture of Poissons and you change it into another distribution. I'll say more about that maybe in my Bayes class, something like that. Probably enough here. But I just want to give you a little bit of intuition on what Poissons are. They're not just distributions, we use them for things. Some of you might know what's called a Poisson process. So waiting times. Waiting times are going to be exponential, and the counts up to some time are going to be Poisson. It's called a Poisson process. It's kind of a fundamental stochastic process for counting things, or measuring waiting times. So very useful in practice. And if things are more complicated, usually we mix over Poissons. So we build this into a hierarchical model. Okay, enough about that. Let's consider another statistic. We also maybe know that the expected value of S squared, which is equal to the variance, but the variance in our case is lambda. So the expectation of S squared is sigma squared. When we're usually thinking about sigma squared representing variance, we have a new name for it. That's lambda. Right there. And so I've got a couple choices in how I estimate something like lambda, or a function of lambda. I could either use, maybe let's just, instead of one data point, let's consider a whole bunch of data points. I probably wouldn't say, well, just give me the first data point and I'll estimate lambda with it. It's not a very good idea. Because the variance is going to be too high. X bar n is also equal to lambda because that thing is lambda. This has smaller variance. We might check what the variance of this thing is. Right here. So the variance of S squared, does anybody know what it is? Remember that thing that I wrote down before? I think I said variance of S squared, and I wrote it down like this. This was going to be
2 sigma to 4 to n.
That's it. That's what you just said, right? Thank you. I was about to blank on it myself. It's that. Right there. So I can rewrite what this is. That's going to be 2 over n minus 1. What goes right here?
Lambda squared.
What's that?
Lambda squared.
Lambda squared. And so in the variance of x bar is going to be lambda over n. Which one is smaller? You can do the mental calculation, but this is your better estimator right here. If you did have n being 1, you might think, well, if n was 1, this doesn't even make sense. So I should use that. But I would say something different to you. If n is 1, you should not be estimating variance in the first place. You have no real basis for estimating variance. So don't let that n minus 1 take over your thinking about this thing. If somebody gave me one data point and said estimate variance, I could do it for you, but it would be driven entirely by my assumptions. So not by the data. I don't like that. I want the data to at least have some say on what I'm reporting. Okay, question is, are there any other estimators out there? Maybe I can do better with something else, and that's what prompted Cramer and Rao, I guess, to think about this. So I'll point out that Rao wrote this down in his thesis. So when he was a graduate student, he derived this thing, and back in the day, your thesis could be like 10 pages. So turn it in, good mathematical result people don't know about. You're on your way. Not anymore. So we don't do that anymore. So you've got to like write it down real cleanly, have applications, lots of test cases, simulations, all of that, and they end up being like 200 pages. Saying that, it's pretty easy to fill 200 pages with a bunch of simulations, some math, and then extend something. So maybe you come up with something truly novel. But all the easy stuff, guys like Rao already figured out for us. So kudos to them. Our life is now harder. We have to do something more interesting. Well, let's just see what Cramer and Rao would have done with this. They would have just said, oh, and I want to point out also, these are both unbiased. So maybe I chose those because they're unbiased, and maybe I like unbiased estimators. So I might have this question, is there a better unbiased estimator? So, and usually I get all bent out of shape when people say things like that, or they say optimal, and they don't tell me what their criterions are. What do you mean? So we'll answer that question in a second. So, but this is still a little bit elusive. Better with respect to what? How are you measuring this? So you should always ask that, optimal with respect to what? So that sounds like a good word, and people walk around and say things are optimal or they're better, but they have a criteria. So always focus on that criterion and ask yourself, does it make sense to me? Is that what I really want to do? Or is there something else I can do? If they've written a really champion paper and made an assumption that has a very easy objective function, you could probably do better and improve on that paper. So maybe think about it from a different standpoint. Okay, is there a better thing? So maybe Cramer Rao says something about this. So Cramer and Rao are going to look at unbiased estimators, and they're going to write down this thing right here. WX. So this is an arbitrary estimator over on the left-hand side. It's just saying all my estimators, my variances for estimators are going to be bounded by what I write down on the right-hand side. So that's just going to be this. Expected value of my derivative. Our parameter now is lambda, right here, log fx given lambda squared. And I'm going to do this for one data point right there. I'm just going to plug in my Poisson function, and I'm going to multiply by n right here because I've got the I.I.D case right here. So everything's I.I.D, I'm going to use that. Simplify my math a little bit. I don't have to carry this sum through everything. So we just need to plug everything in. Oh, and this is inverted. So remember, this is unbiased, so the numerator of Cramer Rao is 1. So now I'm looking over the class of all unbiased estimators and asking if there's anything that's better. Maybe I can put in a little bit of bias and I can look over classes of estimators with a certain bias level. And I can talk about how, if I can improve on that. So Cramer Rao is always specific to a certain bias level in your estimator. Remember that trade-off, that there's always going to be that trade-off. And so what's the best thing you can do? It's hard to say, but if we constrict ourselves to certain classes, then we can talk about what's best within a certain class. So this is going to be our class of unbiased estimators. So in general, we never really know. So it's like maybe I can add bias in a particular way and do better. That's always supposed to be some question that you're asking yourself. And the answer is oftentimes, yeah, you can usually do better. But not always. Okay, so all I have to do is just write down what f of x is and be done, and then it's just a calculus problem. So I'll just write down f of x, given lambda, is equal to lambda x factorial e to the minus lambda. So our likelihood function is only concerning us with this stuff right here. If I forgot the x factorial, I have no problems. I like forgetting x factorial, because x factorial is a pain in a real problem. So when I go to a computer and it's got factorials in it, I usually shut it and think, oh no, my code is going to explode on me. So good thing, playing around with the likelihood function, we don't even need to think about that. We'll write it out anyway. So this is going to be n expected value, one derivative on lambda. There's a squaring in here. I'll just write out what this function is. So this is going to be lambda to the x, e to the minus, oh, I've got a log in here I can't forget about. I tend to do this. It tends to be one of my mistakes that I make when I go through this problem. I always forget to put down the log. The log makes everything easier. Next back to it. So that's a Poisson mass function. I just got one data point in there. I don't have the sum walking through, and I've already factorized out the end.
And that's all inverted, right?
It's all inverted. This is squared. I should finish writing this all out. You guys don't like it when I write out the equation on the board. That was right. So put in my inverse first by n. Make sure I don't have any problems. And so I'm going to take this first derivative right here of the log. So let me just write it out. So the logarithm of everything, this is going to be x log lambda. I'm going to have three terms in here. I'll just write them out like this. This is going to be minus lambda. And then I'm also going to have a minus log of x factorial. This is just one line of stuff I've written on 2 lines. So I take my first derivative of everything, and that thing goes away, as promised. So this is going to be n invert expected value of, now I'm going to take my derivatives of everything. This is going to look like x over lambda minus 1. If you'd like, I can put minus 0. Yeah, there's all, exactly. Let me finish writing the equation.
What's inside the brackets?
Which one?
The x of 1 plus
This one?
yeah, why are they over each other? What's the same?
Spacing. That's just spacing.
Ah, okay.
Minus log x factorial. Okay, cool. So this is pretty easy. Maybe. I'm going to have to think about this a little bit. When I see the squaring right in here, I usually think, can I use that formula over there? Because I can take a derivative easier than I can square out this thing. And if this was not a linear function in x, this could be rather complicated. I will point out that this isn't too hard to work through. But I'm going to just take one more derivative. And I'm going to use this identity right over here. So, it's not too hard, but it's going to expand and be weird when I do this. And I'm going to have a lot of algebra to do. So I like doing this. Minus sign, n. Again, everything is inverted. So that's all the stuff that's the same. Expected value. Now I'll just change some things right in here. So d lambda, one more derivative, and then I don't have to play with the quadratic function. This is x over lambda minus 1. And this will simplify quite a lot. This is going to be minus n expected value. One more derivative on everything. So this is going to be minus x over lambda squared. If you'd like me to take that derivative on 1, I can do that. So a lot of stuff cancels when I use this identity right here. So I almost always go running for this. And now everything is easy. This is going to be minus n, and as promised, this whole thing will be positive. I put those two negatives and I multiply them into each other. So I'll just pull that out, put the plus sign down, and try to keep track of all of that. Expected value of x. Again, this is all going to be inverted, and this is going to be over lambda squared. Expected value of x, we already know what it is. It's going to be lambda, so this is going to look like n lambda over lambda squared inverted. This whole thing will be lambda over lambda. So automatically, I know from doing this, applying Cramer Rao, that x bar is optimal. Somebody clean that up for me. I'll do it for you. If I like unbiased estimators, and I like the L2 norm. So why? Because of that bias variance formula on MSE. So MSE is the L2 norm on everything, and it's decomposed into two pieces. Bias squared. Bias is 0 in unbiased estimator classes, and so the MSE is just variance. So if you like L2, then you like variances. This is the conversation Steve and I were having last time. So this is optimal in the class of unbiased estimators so long as I like the L2 norm. Are there other answers that could be better? Yes, depending on how you formulate your objective function. So if I didn't like MSE and I like medians or something like that, I like the L1 norm and I wanted to be robust to outliers, this might not be my answer. So there's other answers out there. I want to come back next time and just recap Bayes' risk, Bayes' estimators, and we'll probably bounce back to that a couple of times. But it's this double interval formula. And what I want to show you is that Bayes' estimators, and I'll prove this to you next time when we start out, E pi, that's my prior pi, I like to write it in, since Bayes' estimators are averages, I like to tell you how I'm averaging and not hide it from you. But it's the arc minimizer over my estimators, so this is going to be the estimator that minimizes everything over here. Two integrals, I'm going to have a loss function. I've got my parameter. I've got my distribution. I integrate that. This whole thing is risk right here. And then I average with respect to some weights. Bayesians like to call that a krieger, but it's an averaging function. So this looks like a hard problem. It's actually much easier. I'll prove this next time. But this is equivalent to the R minimizer of this function right here, loss, EX in theta, and I'm going to multiply into the posterior distribution, d theta. So this is the posterior. So the thing Bayesians use to do inference. And so I would interpret this a little bit. I would say this thing is equal to the R minimizer of the average, I'll say expected posterior loss. Seems like any time I think about expected values, I end up thinking that funny looking. So, but this is the estimator that minimizes the expected posterior loss. That's how I read that right here. So this is an expectation of the loss function with respect to the posterior. So that's kind of nice. So if I were thinking about this, if I was thinking about the L2 norm, then the minimizer is going to be the expected posterior distribution. If I'm thinking about L1 norm, then the minimizer is going to be the median of the posterior distribution. So we've had this conversation kind of running throughout class, which estimator do we use and why. It depends on your loss function and how your scores are built. And I think that makes some sense. But usually this is a pretty easy thing to figure out. So of course I can build in some complicated loss function and it could get really hairy, but for our typical loss functions, this is usually a direct multiplication. We'll come back next time, prove that statement, show that this thing isn't so elusive, it's not that hard of a math problem, usually, depending on the loss function. And then we're going to move on to Rao-Blackwell notation. That'll take a couple minutes. I think I could spend more time doing some decision theory with you, and maybe that's a good idea because some of you have liked that. And it kind of leads into hypothesis testing. But we need to jump into chapter 8 pretty quickly. So start looking at that. And the big thing that I want you to know about is the Neyman Pearson level. So if you want to start looking at that, that's a good idea. So that's kind of that whole p-value thing. So we're not going to debate p-values in here, but we're going to make sure you understand what Neyman Pearson actually told us, and not the abusive thing that everybody does. Hopefully that will help us make decisions in the future, how we want to treat our hypotheses. That's it for now, you guys. I hope you have a great day, and I will see you on Wednesday. Midterms due on Friday. Marie reminded us that I said Wednesday, but I wrote in the email Friday, so it's right. So let's try to have those done pretty quickly.